The strategy pattern is one of the basic design patterns that allows us to isolate and make independent the logic. That is essentially the same but differs in its implementation. It may sound a bit complicated, but for example, in our application, there are two ways to process payments: payment by credit card and payment through a payment gateway. The logic of these two actions is essentially the same, as both involve processing a payment, but the implementation will be completely different since the algorithms for processing payments through a credit card and a payment gateway will differ. There are many ways of processing payments that differ in their implementation. Hard-coding all these algorithms into the classes that require them is undesirable for several reasons. Firstly, it makes the client code more complex when they need to include the corresponding payment processing code. This makes clients bulkier and harder to maintain, especially if there are several payment methods to be supported at once. Secondly, depending on the circumstances, a particular payment processing algorithm should be applied. Thirdly, if payment processing is an integral part of the client, the task of adding new or modifying existing payment methods becomes more complicated. To avoid all these problems and make the program flexible, independent, interchangeable, and easily extendable, we create a separate class for each algorithm that implements a common interface. Then, when a specific algorithm needs to be used, we select the appropriate class and call its methods. We have four main conditions for implementing the strategy pattern. Abstract strategy: an abstract class or interface that defines methods that must be implemented in concrete strategies. Concrete strategy: a class that implements the abstract strategy. Context: an object that calls methods from the strategy. Client: an object that creates the context and strategies, and passes the strategy object to the context. The use of the strategy pattern in object-oriented programming corresponds to the open-closed principle of SOLID. The open-closed principle implies that classes should be open for extension but closed for modification. Using the strategy pattern allows separating the changeable functionality from the main application code. Thus, when the strategy is changed, there is no need to modify the main code. The client creates the context and strategies and passes the strategy object to the context without knowing which concrete strategy will be used. Therefore, when a new strategy is added, the client code does not change, and only a new strategy class that implements the required interface is added. Thus, the strategy pattern and the open-closed principle are interrelated and used to simplify the support and extension of the software code. It's time to dive into the code and take a closer look at the implementation. And let's start with the abstract strategy. In our project, this is the payment strategy interface, which currently defines one method init, which should be implemented in each payment strategy. The init method takes three arguments: the payment amount, order number, and customer identifier. It returns a promise object that resolves with a URL string for payment. The credit card payment class is a concrete strategy that implements the payment strategy interface and uses an API interface for processing credit card payments. I've written pseudocode based on the Tinkoff API, which would of course look different in a real application. Ideally, to process payments through a bank API, a class should be written that implements the methods of our payment system, and this class could be easily and simply called in our strategy, or ready-made NPM packages could be used. But for the example, let's take the implementation directly, to show the differences in algorithms more clearly. It has a constructor that takes a terminal key and stores it in a class variable. The init method sends a post request to the URL securepay.tinkoff.ru, containing the order, customer, and token data. If the response from the server is not successful, an exception is thrown. If the response contains success equals true, then a URL string for payment is returned. The wallet payment class also implements the payment strategy interface and is intended for processing payments through an electronic wallet. I also wrote pseudocode that looks similar to the real thing, based on one of the providers for processing payments through a payment wallet. It has a constructor that takes 4 parameters and stores them in class variables. The init method generates a URL request using the URL searchparams object and returns it. This URL contains information about the order, customer, and wallet. As you can see, these algorithms differ. In payment via the bank API, we first need to send a request to the API, receive a URL in response if everything went well, and only then show this URL. In the payment strategy via the wallet, we immediately generate the URL and show it. In a real application, of course, the URL would not be generated so easily, since there would be another algorithm for signing this URL and calculating the signature. But in these examples with pseudocode, I just wanted to show you the visual differences in the algorithms for conducting payments through our application. Let's move on to the final class that we have, which is the payment context class. The payment context class is a context that holds the selected payment strategy. It takes a strategy object as a constructor parameter and stores it in the payment strategy property. The setPaymentStrategy method allows changing the selected strategy at runtime. The initPayment method calls the init method of the selected payment strategy and returns the result. The payment factory class is a factory that creates payment strategy objects based on the past payment method. It contains the payment strategies property, which is an object containing predefined payment strategies. The createStrategy method takes a payment method and returns the corresponding strategy. The isSupported method checks if the past payment method is supported. We will cover the factory pattern in more detail in the next video, but for now, we won't dwell on it for too long. The order service class is a service that handles orders. It contains the payment context object, which is initialized with null and then set to the selected payment strategy in the checkout method. The checkout method takes the payment method and the order amount and calls the factory and context methods to process the payment. Thus, the general workflow involves passing the order to the order service. The order service creates a payment strategy through the factory, sets it in the context, and calls the initPayment method of the context to process the payment. All of this allows changing the payment strategy based on the selected payment method without the need to change the order service code itself. But what if a specific strategy requires a method that will not be present in other specific strategies? Should it be declared in the abstract strategy? In the strategy pattern, the abstract class or interface defines a common interface for all concrete strategies. This means that all concrete strategies must have the same set of methods so that they can be used interchangeably in the context that uses these strategies. Therefore, adding a method that exists only in one of the concrete strategies to the abstract class or interface allows maintaining a unified interface for all strategies and making them interchangeable, despite some differences in their implementation. When to apply the strategy pattern. When there are many related classes that differ only in behavior. The strategy allows changing the behavior of an object depending on conditions or situations. When it is necessary to be able to choose an algorithm from several options. When a class has many behaviors presented as branching conditional statements. In this case, it is easier to move the code from branches to separate strategy classes. Using the strategy design pattern makes the program more flexible, convenient to use, and extensible. In particular, applying this pattern can lead to the following advantages. Changing the behavior of an object without changing the object itself. When using the strategy pattern, algorithms are encapsulated in separate classes, which allows changing the behavior of an object using different algorithms without changing the object itself. Flexibility and extensibility. When using the strategy pattern, it is easy to add new algorithms and modify existing ones without affecting the rest of the program. This makes it easier to maintain and develop the application. Reducing code duplication. Encapsulating algorithms in separate classes allows avoiding code duplication and reusing the same algorithms in different parts of the program. Convenient testing. When using the strategy pattern, it is easy to test each algorithm separately, which facilitates testing the entire program. Readability of code. Using the strategy pattern allows explicitly highlighting algorithms in separate classes, which makes it easier to read and understand the program code. Want to learn more about my adventures and ideas? Subscribe to my channel, where I will share my knowledge and inspire you to create something truly great. Don't limit your potential and become a part of the IT Iron Man team that is ready to change the world around them. Welcome to the exciting world of development.